We have a great lineup of talks today. So yeah, let's go ahead and get started. Our first talk is by Niels Mündler about type-constrained code generation with language models. Take it away.
Okay, thank you. Hey everyone, my name is Niels, and I'm presenting this work, which I co-led with Jingxuan, who's also here. Okay, and yeah, in general, it's a collaboration between our lab at ETH and Berkeley University. So, as you may have noticed, AI is being deployed all over the place because, yeah, in all kinds of variations and forms, because people find it useful to speed up code generation because, oops, that's not what I wanted to do. Because LLMs speed up code generation because it allows people to write code even when they're not experts. And yeah, now large amounts of code bases are written by AI and so on. But actually, LLMs, even the state-of-the-art LLMs, hallucinate, make errors, especially semantic errors in code. So how can we make these LLMs more reliable? And that's what we're trying to address in this work using some proper formal systems like type systems, which we developed for humans to prevent a bunch of errors. So can we not directly leverage them to prevent a bunch of errors in LLMs or in LLM code generation? One simple approach to do this, or the direct approach, would be we treat the type system as a black box. We generate code using the LLM. We feed it to the type checker. Type checker may either say, OK, that's good, and we are good to go. We have type-safe code. Or it may give us an error and some additional information. We take that additional information, feed it back to the LLM, and then cross our fingers and hope that the LLM figures out how to fix it. This can make sense, but in general, it has the downside that we don't actually have a control over what the LLM does during decoding. We just have to hope that the LLM figures out how to fix everything. And we can have an arbitrary number of calls to the LLM that are required to actually eventually get some type-safe code. So instead, what we propose is to not treat the type system as a black box, but actually integrate it into the decoding process. The LLM generates code incrementally, token by token, and we know how type systems work. They are formally defined, so we can use them to check the LLM output during each step, and when the LLM definitely makes some mistakes and writes some unsafe code, we can steer the LLM away from that unsafe completion and send it instead on a happy path that actually type checks. So yeah, we leverage that we have full control over the decoding process. We can guarantee that when we terminate, we have some type-safe code. And as I will explain in a bit more detail, we actually only need a single pass, a single call to the LLM. So yeah, previously, type systems have been used to guide the syntactic, like a traditional code generation based on maybe trees and nodes. But what we now want is an incremental type checker that handles the token by token character level code generation. So yeah, let's see. We have an LLM, and we can use it to generate code, which is cool, just on a natural language instruction. Tell it, oh, write a function to check if a string represents an integer, and the LLM goes and writes some code. It starts with the function header and then defines some variables, calls some functions, and in particular, in the last line, it calls parseInt. This is a global function, and this is TypeScript code. This global function expects parameter of type string and will return you the integer that it represents, that the string represents. So starts and puts num, which is of type number, and then a comma. So at this point already, we know that this code can never compile. Like, it will always have a type error. But the LLM is, of course, unbothered by this and just continues to generate code. Instead, we would like a system that actually says, oh, there was an error. Maybe put toString, and now you are actually generating type-safe code. So what we need is this incremental type checker that we can give some partial program, and it can tell us, it can differentiate between, on the left side, code that we can complete to a valid program. You saw that we can put toString and we will get a valid completion. and code that is not completable anymore. It can be as little as a single character that makes the difference. In this case, it's the comma here. So yeah, when we have this incremental type checker, we can integrate it into the LLM decoding process. And on a very simple level, the LLM decoding process just takes a partial program. At the beginning, it's an empty program. The LLM looks at the partial program, gives a probability distribution over all possible next tokens, which are just strings, like a bunch of strings, maybe 100,000 different strings. We get a distribution over which string is the most likely to follow. And then in normal distribution, in the vanilla distribution on the left, we just sample any of these tokens, append it, and continue. And what we want to do instead is leverage some checking, our incremental type checker. We sample a token, then we actually check if we can put this token next. If we cannot, then we want to sample again a different token from the same distribution and repeat until we get a final token. And we designed this incremental type checker in a way that we always remain a valid prefix so that we always can find a valid token that we can put next. This results in the setup where we actually only call the LLM the same time as before, but we just might have to do resampling here. So yeah, let's go ahead and build such an incremental type checker. We start with an automaton that helps us a bit in this construction. And this automaton is a non-deterministic automaton that only accepts well-typed programs. So whenever this automaton is done parsing our program, if it's in an accepting state, we are in a well-typed program. And this is done by basically tracking the abstract syntax tree, and in addition to the syntax tree or the nodes in the syntax tree, track some additional type information like the variables in context, the return type, and the current type of current partial expressions, and so on. So this automaton itself, as I said, it's like a compiler. At the end of the completion, it tells us whether we accept or not, and that's not yet very helpful. What we need is what we call a prefix property on this automaton, which means that for every intermediate state of the automaton, we want to guarantee that we can find a path to an accepting state. And we know that the accepting state is a well-typed program, so if we are in a state that has a path to that accepting state, we are in a state that's corresponding to a prefix of some valid program. And if there's no such state, or if we don't have a transition to such a state, then we know that we are not a prefix of any state and of any correct program, and we reject the state. Let's visualize that a bit later. First, how do we build it? We start with a generic, simply typed language, build this automaton for that. This language is a subset of TypeScript in our case, but the core type system is very similar to a bunch of different languages like Java and Go. And then we gradually extend this automaton with more and more complex features like immutable, like distinguishing immutable variables, arrays, loops, operator precedences, global identifiers, and so on. So that we can cover in the end a fairly big chunk of the TypeScript type system. Okay, so let's visualize what's going on. On the right, we have the code that the LLM has so far partially generated. On the left, we have an automaton, the automaton that we constructed. It's a zoomed-in version. This automaton is quite big. In fact, it might have infinitely many states, but we just look at the ones that we care about now. And in the center, for visualization purposes, I extracted the current type environment that this automaton extracted. So when we start, we see only some global variables. In this case, it's parseInt, which takes string, and it's a function that returns that takes a string and returns a number. And as the LLM goes and generates the name of the function, we go through the automaton as well, and then we parse the parameters. And after we completed the first line, we actually update the type environment. We get the parameter text, which is of type string, and we get the function itself is int, which takes string and returns Boolean. After the second line, we get this variable num in our context, which is of type number. And we forward a bit more again. Eventually, we arrive at that state that I described earlier, where we're calling parseInt with a variable num as a parameter. And yeah, as you can see in the automaton, we have only continuing state transitions that corresponds to well-typed completion. So we cannot put a comma, because a comma would not result in a well-typed program. But we can, for example, access some members. So when the LLM now tries to add the comma, we know that there's a type conflict. We don't have a transition in our automaton, so we reject this token. The type conflict comes from, as I pointed out again, parseInt taking a string and num having a number. Yeah, instead of putting this comma, which we have rejected, the LLM then infers, we sample then toString from the distribution, which is actually valid because we have some transitions in the automaton that allow transitioning there. And after this correction, the LLM figures out a correct solution to our problem. OK, that's all nice and good. So we solved the issue that we had in the beginning. But yeah, this automaton, in a bunch of places, very straightforward. There's one situation where it's a bit tricky, and that I skipped. Yeah, that I skipped over. Let's have a closer look here. So when we call parseInt and we have that part num, I told you that we want to determine at this point already whether this is a partial program or not. It may be that actually num, which is of type number, cannot be in any way converted to a string. We don't know that at this point yet. We need to solve something that's called the type inhabitation problem, or at least we need to address it. And in particular, we want to figure out if there's any textual completion that can turn this type number into a type string. And what we do for this is we know the type of the partial expression, we know the type of the goal type, and instead of now searching over all kinds of strings, we lift everything to the type level, and we search over different operators that we can apply to types and get something like this, which is a type graph on which we can do a type reachability search. So we start from our type num, and now we search through operators that we can append on the right. For example, we can do this member access toString. This member access is finite. And we can call is finite. We recursively search through this graph until we find the desired type string. And at this point, we can determine, oh, nice, yes, we can actually turn this into a string. So this is a valid partial expression. So the whole partial code is acceptable and can become a well-typed program. Yeah, there's some more tricks here. Like we need to bound this whole graph to be finite to actually make sure that we terminate at some point. But we do this in a sound way so that we can always guarantee that there's some well-typed program, though we might remove some non-well-typed programs. OK, so recap. We have this setup, and we have these benefits. We have only one forward LLM inference pass, no backtracking. We guarantee the type safety once we terminate. We fully leverage this type system. And downside, we had to manually actually build all of these automata. But let's see if the work paid off. We evaluate on 6 different language models from 2 billion to 30 billion in size, 4 different language model families on 2 popular function generation benchmarks in the ML community. These are all benchmarks that require the model to write a single function, and in this case translated to TypeScript. We have synthesis, which requires the model to write a program from scratch. Translation, which gives the LLM the Python translation and ask it to translate to TypeScript. And repair, which gives the LLM a previously unsuccessful run and then gives the compiler feedback. And after that compiler feedback, we additionally constrain in our type constraint system to see if we can get additional benefits beyond this feedback loop setup. And yeah, we compare then the vanilla constraint decoding with a type constraint decoding to see how many of the errors we can eliminate this, with our method. If we look, for example, at Quen 32 billion, we reduce actually the errors quite significantly, over 60% in all the settings. And this also holds for smaller models, maybe not as extreme, but we reduce even for the 2 billion model over 50% of the compiler errors. And overall, we see for all models a drastic decrease. Now, we would expect that we get a strict improvement on all of these settings because we never actually change an output when it correctly compiles. But yeah, beyond that, we can see that there's actually a quite drastic improvement here in the reduction of compiler errors. So does this also hold true for functional correctness? Before, we only looked at the at these type system errors, but we didn't actually make any statements about functional correctness, like does the program do what we want it to do? And we find that yes, it seems that we do have some improvements of several percent on all the different settings, and in particular in the repair setting, which is basically all the hard problems where the model failed on the first pass. And now, in addition to the compiler feedback, our type constraining gives even more guidance to the model to resolve these errors. And if we looked at some of this closer, and often the model just doesn't figure out how to solve the error, but with the constraining, we force it to fix the error. So in this case, we get these large improvements of like 80%, especially for the small models. Okay, so yeah, that's nice, but a lot more needs to be done. So we do not yet cover all the TypeScript features, like we don't cover user-defined classes, for example. We have constructed this now manually for TypeScript, but there's a bunch of different languages in the world, and we would like to cover all of them. So maybe for Go or Java or even more stronger type systems that give us more guarantees, like Rust, would be a very interesting target to build such incremental type checkers. And maybe we can even generalize a bit and say, oh, there's a bunch of type systems for which we can generally, maybe even automatically, derive such incremental type checkers, whereas maybe there are some features, maybe we cannot borrow check incrementally. I don't know what Rust does. So it would be interesting to have some like more theoretical results there as well. Okay, so as a conclusion, LLMs make semantic errors and make errors during generation, but we can resolve a lot of these using an incremental type checker that's based on basically automata that parse the output during generation. And yeah, this works. We reduce compilation errors quite a lot at the end. Okay, thank you.
Okay, thank you for the talk. We have around 2 minutes for questions. So yes, in blue. Could someone give them a speaker, a microphone?
Hey, nice talk, and I'm a huge fan of this approach, and I wanted someone to do it for a long time. But the question I have basically is, have you considered exploring not just one pass tree autonoma, but like a search tree of possible paths to find somehow better solution? Because I assume, let's say, LLM generates an output, right? But there are many possible outputs if you don't pick only the first most probable, but maybe 1, 2, 3, I don't know, small number. Yeah. You can explore some small exponential subspace.
Yeah, there's some, I mean, I've considered this, and there's some very rough work in progress with the student on this. But essentially, we found that like you can basically do this tree, and then you maybe need to actually give the model some additional context on why some trees are wrong, because it often converges even in different branches of the tree to make the same error again. Yeah, but you could also combine this with beam search or any other basically search algorithm, and it should work. Yeah. Thanks for the question.
One more question. Yes, over there in white. I know there's lots of questions. Maybe you can find the speaker after.
Yeah, thanks for the great talk. And my question is, you only considered one type system. And I think the type system of TypeScript is quite core That is, any number is a number and any string is a string. But when we think about a Rust type system, there is a bunch of other, bunch of various types of strings, and there are a bunch of other kinds of numbers, and like integer 32-bit and 64-bit. So my question is, when we are implementing this strategy to the other more fine-grained type system, do you think it's going to guide the LLM like this well, like this approach?
I think so. Like even in TypeScript, we implemented some kind of like type super subset settings, and basically you have this in integers, right? That you have the numerical constants, maybe a super type of all the different lower, like finer grained integers. And if you add, I think this kind of support should be addable to this, though no guarantees.
Our speaker one more time.